Well, hello, and welcome to today's Micron Valued Partner webinar. Better performance and less complexity with Microsoft SQL? Yes, with Micron Enterprise SSDs. I'm Matt Wokus, Strategic Marketing Manager for Micron Storage, and I'll be your moderator for today's webinar. Now, before I introduce today's presenter, we just have a couple of reminders. You can submit questions at any time during the presentation using the Q&A tool, and I'll ask those of our presenters during the program. And also, if you have to drop off before we conclude, I'm sorry, but remember, this webinar is being recorded, and you can watch it on demand within an hour of conclusion using the same link you used to log in today. So today, we actually welcome back one of our returning champions of these MVP webinars, Doug Rollins, who is our Senior Technical Marketing Engineer for Micron Enterprise SSDs. Hey, Doug, thanks for joining us.
You bet, Matt. Last one was fun. This one should be too.
I'm looking forward to it.
You and me both.
Yes. Now, I know you're talking about SQL workloads, and there's many of them that can benefit from flash storage. Which ones are you going to talk about today?
Well, you know, that's a good point. When we think about SQL, many of us often gravitate to one of sort of two distinct camps when we think about a workload. The two are shown here, either OLTP, Online Transaction Processing, or I've abbreviated Business Intelligence Decision Support Systems as DSS, because frankly it's too long to fit in the little square there. Just a quick side comment. Matt and I recognize that there are many other workloads to which SQL regularly gets applied, but for the purposes of this webinar, we really wanted to look at these two specifically. The reasons for that is they do tend to sit at opposite ends of the spectrum in terms of how they access disk systems. And so Matt and I were thinking that it would make sense for us to look at two very commonly deployed SQL workloads and then look at those in the context of how SSDs can benefit. To start with, for those on the webinar not already intimately familiar with the acronym OLTP, like I mentioned earlier, it stands for Online Transaction Processing. And ways to think about Online Transaction Processing or an OLTP workload is it's really transaction focused. And so if we look at some common ways that that's deployed, some real world examples of how people use this type of an access mechanism, things like sales and order placement. So often a sales order will be a relatively small transaction. Typically they're read more often than they're written, and typically because we don't have a lot of predictability when it comes to the way sales orders come in, they tend to be very random. Same thing with web services or statistical processes. Any of these are usually relatively small elements of data. They typically have about twice as much read as they do write traffic, and you never know what record is going to be accessed and what order they're going to be accessed. So again, they do tend to be very random. So we can generally think of OLTP as a relatively small transfer. Roughly, we read 2 of those for every 1 we write, and it's really 100% random. You never know what record is going to be accessed next. Some of the key imperatives around that, particularly focused from our customer perspective, is latency. IOPS are great. IOPS are wonderful. Years ago, we used to brag about IOPS when SSDs were new. But since the market's matured, the expectations matured, and the focus of what's really important in an OLTP workload has been sharpened quite a bit. And the focus really is around latency. Getting those transactions in, processed, and out quickly is important, but we also don't want to have any excessive lag time for any individual transaction, and we certainly don't want to have any outliers, transactions that get put off while others get executed. As I mentioned earlier, the transfers themselves, in terms of what gets read from or written to, are typically small, and again, they're very highly random. So this is kind of a 20,000-foot laundry list of what characterizes an OLTP type workload. Now, at the other end of that spectrum is a business intelligence or decision support systems workload. And there's lots of different ways that BIDSS is known. It's kind of the common umbrella term for any sort of an algorithm or execution mechanism that aids either a data analytics engine or staff to help make some choices about what to do in terms of business choices, like where and when to introduce a new feature set, or whether or not to buy a certain building that has certain characteristics. But at the end of the day, the workload itself is very research oriented, and I give a couple more examples there. What if scenarios, that's another popular one, where we're trying to figure out, if I do X, what are the implications? If I do Y instead, what are the implications? The focus on business intelligence and decision support system, it's almost the opposite of OLTP, where in BIDSS, the focus is really about storage throughput, very large transfers, and we're looking for high sequential I/O placements. We're looking for a very fast throughput from our disk subsystem. So what's interesting is we would think intuitively, or at least many of us would, that BIDSS workloads in Microsoft SQL are really optimal for use with a spin drive. Rotating media tends to be very fast when we do a sequential transfer. But what's interesting and was surprising based on some lab research we did is that's often not the case. And we'll take a look at that in a little bit later. So let's start by... Sorry, go ahead, Matt.
All I'm saying is the difference between the two is with OLTP, it's really the latency, because you're wanting to read that short amount of information quickly, but it could be a random occurrence that's going to happen.
It's almost always random.
Yeah. Whereas the big data, or would the business intelligence, would this be considered big data analytics, or is that something different?
No, they're not exactly orthogonal, but they're not exactly congruent either. Usually BIDSS is about mining something like a data warehouse to figure out, based on some historicals, could be structured data, could be unstructured data, but it's more specific than the sort of the big data umbrella. What we're really looking for out of a BIDSS platform is help us predict what our optimal choices are going to be amongst several choices. And like I mentioned, it could be what feature to introduce when, what building to buy, what's going to happen if I do X instead of Y. So again, it's not the opposite of big data, but usually they don't always walk hand in hand is probably the best way to put it. But gotcha. the net of it, think OLTP, small random latency. BIDSS, large sequential throughput. I mean, those are really the key differentiators from a storage perspective on the differences between the two. So
makes
if we
sense.
Start digging, go ahead. Okay,
so that makes sense.
If we dig in a little bit, let's start with OLTP. And I'm waiting for my slide to come up. There we go. So OLTP is kind of interesting because within an IS group or within a software group, we often have different teams whose needs, frankly, are at odds with one another. If we look, for example, at storage administrators, the storage administrator, that's the person or persons who are charged with, hang on, we've got a little bit of a technical glitch here. Let me advance to the next slide. There we go. So with storage admins, their responsibility is really exactly what it sounds like, administration and maintenance of storage within the IT platforms. They end up provisioning and maintaining it, so when someone needs storage, it's the admin you would go to. I need this much capacity and this much performance with this kind of protection level. They're also responsible for maintenance, which would include simple things like break, fix, repair, but also patch installation and that kind of thing. And ultimately, they're also required to manage the storage platform to anticipate the unanticipated. And that sounds kind of strange, but they're often tagged with having to meet unforecasted demands. So out of the blue, a requirement for a given capacity or protection level for a surprise project can come out of the woodwork, and it's really the storage admins on whom that lands. Now, they have their own focus, and since we're talking about SQL, we'll take a look at DBAs. The DBAs, or the database administrators, they're really the ones, Matt, are you bumping the slides?
Oh, to database administrators? Yes.
Okay. So with the DBAs, their focus is really about installing and configuring the database itself, maintenance, upgrades, monitoring performance, that kind of thing. And they're really responsible often across all the corporate databases. So, on the one hand, we've got the storage admins who are setting up the storage for the DBAs, but on the other hand, the DBAs have some very particular requirements. And what ends up happening is it's almost like the irresistible force meets the immovable object. We have often competing demands on each side of this, and each of them are critically important to the enterprise, but these two groups often, frankly, don't see eye to eye. But there's an exception. They do often have a common goal. They often see eye to eye on these two high-level requirements. They both would like to be able to simplify the systems and the tasks with which they deal, and when possible, they'd like to consolidate. Both of those are interrelated. The simpler we can make a system, the more consolidated it is, and the more we can consolidate, frankly, the simpler the system ends up being. So if we take a look at simplification and consolidation, here's an example. This is kind of a theoretical example. Over on the left, we have a massive shared storage platform. This could be any sort of a SAN or a very large filer or a large-scale NAS system. But the point is it's quite large, very high performance, quite complex. Left side of this is sort of the storage admin's domain. And over on the right-hand side, we have a database or a couple databases. And traditionally, we've taken the left side and we place it on the right side. That is, we often take our legacy OLTP deployments and we end up dropping those onto our SAN. And what we end up with, it kind of looks like spaghetti. Because remember my comment earlier, DBAs have certain requirements around storage types. They may require speed out of one LUN and a high level of protection out of another, and a compromise in speed and protection and volume on a third. Sorry, go ahead.
Well, no, so is that also then physically where the LUNs are on a hard disk drive makes a difference as well?
It does. When we think of SANs and large NAS filers, the logical unit that we're talking about often spans multiple physical units. So, for example, if we needed protection and speed, we might span 4 physical units and create a RAID 10 array. On the other hand, if we needed protection but we didn't need quite so much speed, we might span 3 physical units and do a RAID 5. If we need not so much speed but protection, we do a RAID 1. And the list goes on to where on the software side of the house, your DBAs are going to have certain requirements around LUN sizing, protection levels, and performance. And your storage admins are going to make certain requests about, well, geez, can't you just kind of put it all in one spot instead of in, 1, 2, 3, I lost count, multiple spots. If we look at the elements of SQL, like the data itself, tempdb, and the log, we may even end up placing each of those elements of a single database on different physical LUNs with different performance and protection levels. With multiple databases, it gets more complicated. And what you can end up with when we place SQL on these large-scale SAN or NAS filers is this spaghetti-like concoction that we see here where each element gets mapped to somewhere else. And it gets worse. If we want to have high availability in our storage, we're going to need 2 of these things. And each one of them we're going to have to carve up into multiple LUNs of multiple sizes, multiple protection levels, and we're going to end up mapping multiple elements to multiple LUNs for backup purposes, for protection purposes, for data durability purposes. So one's bad enough, but when you want to run parallel SANs, it actually gets even uglier. Was there something you wanted to throw in there, Matt?
So wouldn't you have this issue also with SSDs?
That's a funny question. The short answer is when you want to simplify and consolidate, SSDs are often a really good choice, and there's a distinct reason for that. What I'm showing here is that an enterprise-grade SSD is capable of absorbing all of these different placements, whether it's the data, the temp DB, or the log, either on a single drive or multiple drives. And the reason for that is really pretty straightforward. In the case of enterprise SSDs, we have to remember that every I/O that's performed against the SSD is like every other I/O. And what I mean by that specifically, let's say that we have a highly random access set, like we're accessing our main data set. If the data lives on one portion of the SSD, or let's say it's spread across the entire SSD randomly, SSDs with no moving parts, they can access any part of the data anywhere on the drive with equal speed. So what we don't have is we don't have the delay of waiting for the head on the spin drive to swing from, let's say, track 12 over to track 320 to get the next data element, and then back to track 16 and then to track 61, and that bouncing of the heads back and forth to handle a random data placement it really kills your performance and increases your latency because you have to wait for the heads to move every time. SSDs, we don't have that problem. We don't have any moving parts. So for us, whether it's placing a log, reading a log, using tempdb or scratch space or the main data element, it doesn't matter. Every I/O is just like every other I/O, and there's no speed penalty to pay for random or sequential placement. With larger SSDs, like if you have a card form factor like our 420M, you can actually place multiple databases on the same physical unit. You can drop, whether it's completely discrete workloads or similar workloads, it doesn't really matter. Because of that equal ability to access any portion of the SSD, the same performance level as any other portion, we've effectively eliminated noisy neighbor problems. Noisy neighbor problems often drive us to even more complex deployments where if we have we can't really share physical drives between databases if their workloads are very dissimilar or they're very busy. If they're busy, they're considered a noisy neighbor, and they interfere with one another and bring the performance of both sides down. We just don't see that problem when we move over to SSDs. So if we take a look at a real example of this.
Yeah, that's an interesting point. I just got a question here that just came up.
Oh, yeah.
That, but when using SSDs, do you have to change the way you think about designing storage for like a production SQL server?
So make sure I understand the question. I think what it's saying is there anything special that we have to do, whether it's database tuning, query tuning, or any other way of standing on our head to make it work with flash drives? That sounds right?
I think so, yeah.
Well, this real-world example is a good answer to that. Our own IS group, who is responsible for maintaining, managing, designing, deploying the systems within our fabrication facilities, they were looking for, frankly, a much smoother and lower latency method of doing wafer inspection. For those who are outside of the semiconductor business, these wafers, these silicon wafers, imagine a serial process where you've got effectively, a truck of sand coming in one end of the factory and you've got wafers coming out the other end. If anybody's here from production, I know I'm grossly oversimplifying, but the idea is that it's kind of this long assembly line. It's multiple steps, and each step depends on the previous step. And if you can imagine this long string of product that's going from raw material to completion, and if at any point in that process we slow things way down, the stuff that's upstream isn't going to wait. I mean, some of these processes are very time critical, and you really can't just push a pause button while you wait for something to happen. And so what our IS group was looking for is a way to both drop the latency and make it more consistent for one of the steps in wafer manufacturing. We use SQL on the back end for maintaining the data and making some comparisons to check the stuff as it goes down the fabrication facility manufacturing line. And IS had gone with a relatively complex and expensive mechanism of trying to get that latency under control, which I'll show you in a minute. They had gone through and tried to do some query optimizations, and they were successful, although not successful enough. And this quote here from Steve Taylor. Steve is our Enterprise IS Architecture Director here at Micron, and this is a direct quote from talking to Steve about when they were using parallel multi-port fiber channel attached SANs. And I'll read it to you so I make sure I get it right. Steve said, "Latency is king. It can enable a multi-billion-dollar fab to run precisely, or it can bring it to its knees." And the point of that is what I was describing earlier with that long line of stuff in various stages of completion. If at any intermediate stage you have an excessive latency spike or your latency is too high overall, you're going to slow everything down. In high volume manufacturing, that's a real problem.
It's just like a car driving too slow on the freeway.
It's like a car driving too slow on a one-lane road.
Yes.
The other cars, you can't get around it. It's a serial process. You can't trump a given car that's towing the boat so that your Porsche can get around it. It just doesn't work that way. It's a one-lane road. So what IS did, and by the way, the workload we're talking about for IS is classical OLTP. It's classical small transfer, read to write 100% random. What they ended up doing was they made a switch from what they were doing to SSDs in commodity off-the-shelf server platforms. So they migrated from a multi-port, even flash accelerated, but multi-port fiber channel attached SAN, off of that over to a pair of 2U2 socket servers. And that was the only change they made. If you look at the chart right there, you can see that blue vertical line was where they made the switch. Over on the left of that blue vertical line is where we were at in latency in milliseconds using SAN. And to the right of the vertical line is the same measurement on the same facility running the same volume, but after they moved over to SSDs in these commodity servers. And they saw a 10x improvement in the latency and the response time of the application, which is huge. In a manufacturing facility, you may have unforecasted demand. You may have a spike, and you need systems that are designed to handle unforecasted demand. And here's a classical example of a system that the newer version, the SSDs in these 2U servers, is designed to handle spikes in demand because it has a 10x improvement in performance. The team was running kind of at the hairy edge when they were using SAN, and when they migrated to SSD, they had significantly more headroom to absorb that kind of input. And if you look at the quick summary of what they said and what we did, again, here's another note from Steve, and I'll read this one so I get it right. With SSDs running in an off-the-shelf host, we see a 10x performance improvement at 1/4 the cost, same databases, no tuning. So they took the exact same databases, the exact same queries, and they moved them from the SAN over to this pair of 2U2 socket general purpose servers that had SSDs in them. They made no other changes, and the other good benefit was it ended up costing them about 1/4 as much. So what we saw was this drop in complexity and a drop in cost, and this picture kind of wraps it up. So here's what our IS team was doing. I mentioned earlier parallel SANs. They did that so that if something went awry in one of them, they didn't have to shut the system down, the fab down. And this was a production level Microsoft SQL database. So they went from that to this. So what we have here is the 2U2 socket commodity servers. Within each server, it's loaded with 24 SSDs, and the SSDs are carved up into 2 LUNs. The LUNs are identical. They have exactly the same performance, exactly the same latency, and the level of performance and the low latency is more than 10 times better than what they had before. So our DBAs are happy. Our DBAs only have 2 LUNs per system, and they're identical. And they have identical performance. Our storage admins are happy because they only have 2 LUNs per system, and they have identical performance. And the DBAs aren't bugging the admins. Hey, I need a faster LUN here, a bigger LUN there. I need less latency over here. This design, this commodity off-the-shelf plus enterprise SSD design, just was frankly an order of magnitude literally better in terms of latency. And like I said before, same databases, no tuning. So to answer your question originally, I know this was a long delay in getting an answer. No change. The only change here is we have a much simpler system. It costs less. It has 10 times better latency. They made no changes to the underlying database, no changes to the underlying queries. So in a nutshell, you get everything they wanted and more. The other nice advantage of going with this is from a support perspective, and I don't highlight that here, but it was pretty important to the IS teams that support the fab deployments. Because these SSDs look and sound and smell just like hard drives from the host perspective, the support's exactly the same. If one of them fails, the light on the front changes color, tells them which one to replace. They literally take a replacement unit, put it in the system, and it starts rebuilding automatically. I mean, it's just like a hard drive from the support staff perspective. So it's even better. What did they end up with? They ended up with making this migration a 75% lower CapEx budget. They got 10 times better consistency in terms of the latency reduction and latency consistency, and obviously much simpler administration from both sides of that equation, from the storage admin side as well as from the DBA side. So that's kind of
I got a question.
Yeah, fire away.
I got a question here. So you've got we definitely got performance I/O boost and the space savings, but what about long-term risks? Won't SSDs wear out faster by shouldering so much of that workload?
That's an excellent question. So SSDs absolutely do wear. However, they warn you way ahead of time before they're worn out. So all of our enterprise drives have a wear indicator that tells you how much of the drive lifespan has been used. So you can add that to your normal weekly monitoring functions, and you can determine well in advance of when they're going to wear out. You can schedule a replacement, and again, because it's supported like a hard drive, I don't have to schedule downtime, right? I can just pull it out while it's running. The hot spare takes over, put in a replacement, it automatically rebuilds itself. So do they wear out sooner? It really depends on how much work you're throwing at them. SSD wear is a function of how much write traffic you send its way. So if we have a database that is relatively inactive, they tend to wear out probably, it would take longer to wear them out than the useful life cycle of the platform they're installed in. I did a session, it was last year, looking at SSD wear specifically, and found that if you budget around a 3-year life cycle for your platforms, or even a 5-year life cycle, there are production level workloads which enable the SSD to last far longer than that before reaching the total bytes written amount. So I don't know if that answers the question, Matt. It's kind of like how long is a piece of string? Well, it depends. Do they wear out sooner? Well, it really depends on how much write we're throwing at it, how much traffic, how busy the database is. There's a lot of variables in there. So it really depends. In this case, they were not sending enough write traffic that wear was really a concern, or wear within a certain time frame was a concern. If you want to know more about what our IS team did on this, there's a couple public documents that are kind of interesting to look at. We have a video. There's a hot link there. I'm not sure if that comes through, but I believe it's on the resources page if it doesn't. There's a video interview with Steve Taylor, who I mentioned earlier, and Mike Cunliffe. Mike is a storage architect, DBA architect, really responsible for designing the future of what the fabs do in terms of the IS functions. He's in there. And then if you want to read rather than watch, there's a link to a case study. So we did a case study on this that focuses in far more detail than we did here about exactly what they did and what they got out of it. So that's a good real-world example. We'll talk a little bit more about OLTP, but this time it's really from more of a research data perspective, and it's what you can expect out of OLTP when you move over to Flash in terms of transactions per minute and new orders per minute. So these are some classical metrics. In this case, our application acceleration engineering team, it's a team we have devoted in the Texas area whose sole job function it is to determine what sort of application acceleration you get. These are real benchmarks measured with an app. They're not synthetic. They generate real workloads on real databases and send them through the real storage engine and the real database engine And what they get out the other end helps characterize what we can reasonably expect to see when we look at SSDs. And what is it we wanted to measure? So this drive's a little bit different. This is actually a PCI Express drive, even though it's a 2.5-inch form factor. If you're not familiar with the 2.5-inch form factor, it was a couple of years ago, wasn't it, Matt? SFF 8639 was adopted. Maybe it was longer than that. Maybe it's 3 or 4 years ago. But regardless,
I'll check Wikipedia on that one.
Yeah, sorry. It's been a while. So it's a standard form factor. There's quite a few folks producing drives. We have our 420M in this form factor. But in a nutshell, it's real PCI Express. It supports hot swap, hot add, just like any sort of hard drive or SATA or SAS drive would. So it's very convenient. We also knew that because it's PCI Express, it should have a significantly higher performance. And we want to know how high. How hard could we really push one of these PCI Express drives with OLTP? And we were going to measure both NOPM and TPM. We would also decide to take a look at latency. We talked earlier about how latency is really a key imperative for OLTP. And we fired up one server, we put in one drive, and we created 160 virtual users, all hammering the exact same back end at the exact same time. And here's what we found. So again, this one of our P420Ms and 160 users, we were able to generate north of 2.5 million transactions per minute, while generating north of 500,000 new orders per minute. And what's interesting about this metric is this is one physical unit, one physical SSD in one physical server. And it's pretty impressive when you think about 2.5 million TPM off of that one single drive. We should also note that we sized the database and the access parameters such that we made sure we got disk I/O. So if there's any curiousness about was this an in-memory process, it absolutely was not. When we took a look at latency, this one was another shocker. We expect read latency is always going to be low, and with a vast majority of enterprise flash drives, it really is. But write latency, that's often where SSDs, even enterprise SSDs, can kind of fall a little bit short. So we took a look at write latency. What we're seeing on this graph, on the x-axis is time, increasing time from left to right. And then on the vertical axis is latency of a write response in microseconds. The two left bars, which are start really high, then drop, those you can kind of discard because that's during the ramp-up time of the exercise. So this is really getting all the engines fired up and running at full speed. And what you see is after we pass through ramp-up, if you notice, the write latency on that is incredibly low. In fact, it's less than 1 millisecond. And remember that it stays less than 1 millisecond with all 160 users hammering the system all at the same time. And it's just one drive. It's pretty amazing for just one drive. So we had taken the one P420M PCI Express drive and had generated a tremendous amount of I/O at the application level, not at the synthetic level. But these are actual TPMs and NOPM that we see reported out of an app, all of which had less than 1 millisecond write latency. Pretty good stuff. So then, if you want to learn more about that one, there's a link there. I think it's also on the resources page. There's a tech brief, talks about the setup, the testing mechanism. The plots and the charts are far more detailed. So if anybody has any curious about that, you want to learn a little bit more, I'd encourage you to take a look at that tech brief.
So why would you choose, so this is great for all the OLTP stuff or workloads. So basically, why would you go with a SATA interface versus PCIe?
It's a good question. Primarily because of latency. Secondarily, because depending on the PCI Express drive, it may have significantly more horsepower internally, more channels on the controller, or more NAND that it can access, which gives you much better throughput. The interface itself gives you better latency. We have far fewer transitions between protocols and interfaces and drivers, and it's a much more direct path into the NAND than it is through SATA. So you kind of get both.
So you get much better latency with the PCIe, but I guess it would be ease of use with the SATA interface.
Exactly. I mean, SATA, and SAS for that matter, are ubiquitous. Every system out there has some sort of SATA interface. There's a plethora of ways of creating multiple device virtual disks out of SATA. There's a plethora of ways to do RAID or ZFS on top of them. But yeah, it's ease of use and ubiquitous. The deployment's ubiquitous. The knowledge base is ubiquitous. It's kind of funny with the 2.5-inch PCI Express. The drive vendors are kind of leading the chassis vendors. There's multiple drives on the market, but chassis are just now coming out to market. Dell's had one for a couple years that supported 4 of these devices in a 2U2P, and they were the only system vendor for quite a while. But I understand there are several other system vendors who are getting on board and will be shipping platforms pretty soon to support it. Does that help? I mean, that kind of draw some lines there?
Yeah, I think that helps with the positioning of where you go with each, one interface versus another.
Yeah, exactly. So if you're looking for a retrofit, and you want hot swap, you're really thinking SAS or SATA. New build-up deployment with hot swap, 2.5-inch PCI Express is a good choice. If you don't need hot swap, PCI Express card form factor is a good choice too. At the beginning of this, I'd mentioned that there were 2 workloads on which we wanted to focus, OLTP and BIDSS. So let's make a right turn a little bit, and we'll talk about this other workload, business intelligence and decision support system, how SSDs can benefit that. I'd mentioned earlier that it's almost intuitive to think that because of this large block sequential nature of the workload, that a rotating drive will do as good or maybe even better than an enterprise-grade SSD would in this type of workload. So we wanted to find out. I mean, this is another one of those conventional wisdoms that you end up questioning. Again, we sort of tapped our same team in Austin, the Application Acceleration Engineering Group. We wanted to find out if you could build this modular, scalable BIDSS platform using SSDs and, frankly, see what you get. If you build it out with flash drives, what do you get? And so the focus on determining that was we used our M510DC. For those of you not well acquainted with it, this is a 2.5-inch enterprise-grade SSD. It's up to 960 gigabytes in capacity. SATA interface, so it plugs into a SAS host or a SATA host, doesn't matter. Supports full hot plug, full hot swap. When we did the testing, we sent it multiple concurrent, very complicated business-related queries. So we had a significant number of users would fire off all these complicated queries in different order with different timings, really to simulate a bunch of people hitting that BIDSS back end to help them make some of these better choices. And the database that we used, again, big enough so it does not fit in memory, guaranteeing that we're going to get disk I/O. We use a standard 2U2 socket commodity off-the-shelf server platform. So from a hardware perspective, nothing special at all. We use Microsoft SQL, again, and we applied the stimulus directly to it. And there were 22 of these relatively complicated queries in the I/O load. And again, applying directly to SQL, and we did it in a random order. We looked at one user, so simulating one person asking a lot of questions, maybe in preparation for some sort of a board-level report about what we ought to do with our business. And we also looked at 6 users. Now, knowing 6 users firing off 22 queries was going to create a pretty tough workload on any back end. We thought it'd be interesting to see what that platform did with those as well. And just again, a quick note that the database was sized to make sure that it didn't fit into memory. So what did we find out? Well, we took a look at these 1 user and 6 users, and we built the back-end platform 3 different ways. We started out with 12 15,000 RPM enterprise hard drives. That was kind of our baseline. This is what we thought would do pretty darn well with this type of a workload. We also compared that to a dozen M510DCs configured the same way with the same database, and then we shot in the middle. We cut the number of them in half. So we end up with 6 data points. 6 users on each of 3 configs and 1 user on each of 3 configs. And what we're looking at here is a direct measurement of how long we have to wait for all the queries to complete. So on the x-axis, we've got user count and we've got storage type. You can see it's color-coded on the right there. And on the y-axis, we've got seconds. How long did we have to wait for the queries to turn? The dark red is our spin drives. So these are the 15,000 RPM enterprise disks in a 12-drive disk array. And this is the one we thought was going to do pretty well with this large block sequential workload. When we swapped it out, we measured that, obviously recorded it, and then we went over to just 6, so half as many, M510 DC, same database, same mechanism, same user, same everything. The only difference was swapping out the storage. And you can see here what happened to the average wait time. In particular, look at what happened with the 6-user average wait time. So this is a very busy system. This thing is getting a lot of queries run against a large database, all randomly, all simultaneously from 6 different I/O streams, from 6 different users. And you can see the significant drop. When we went up to 12 drives, we got it to drop even further. Over on the right, this is our 1 user, like I said, maybe preparing for some sort of a board report, or she's got to make a recommendation to the VP on what new feature to introduce when. We got a significant advantage there too. So our query rate times dropped. And depending on which one you look at, which drive count you look at, the drop was anywhere from 75 to 86% faster. So that's on the six user side, because that had the biggest difference and really simulated more of a common deployment method. So it kind of begs the question, that's a surprise. We don't expect to see that. We expected to see a tie. And so then we got to wondering why. What is it about the platform that enables that lets the SSD do so much better in a workload we normally associate with hard drives excelling in? And the answer there is we found there's a direct tie between the throughput, the large block sequential throughput of the storage platform, and how responsive the queries are. In particular, the faster the storage system, the faster the queries come back. Made a lot of sense. But when we looked at the actual numbers, by the way, this data here is laid out similarly. The vertical axis in this case is megabytes per second, total throughput for the storage. We've got 1 user stimulation on the left. We've got 6 user stimulation on the right. And we've got color coding to indicate what the storage config was. But what's interesting is this one's inverted. So in this case, a taller bar is better. And you can see that with 6 users stimulating 12 M510 DCs, we have a significantly higher throughput than any other configuration, and every SSD configuration is significantly faster than the hard drive configuration. So again, this one was a little bit of a surprise. We expected that rotating media would excel here, but what we found was just the opposite. What we found was that the flash drive arrays did much, much better no matter which one we picked. So again, the comparison was between our new 510 DC. This is a really read-centric drive. It's aimed at this type of a workload versus high performance. You can use that term with hard drives, high performance hard drives. The query time, 75 to 86% faster, depending on which configuration we looked at. And the storage system itself had about 5 times the throughput when we went to SSDs instead of spin drives.
So, any thoughts on why it came out faster? I know it wasn't intuitive, but is it because noisy neighbors, or is it that?
No, the only thing I can think of is with SSDs, and especially read-centric SSDs, it doesn't mean you can't write them. It means their design is really tailored around, say, 90% read, 10% write. So they're really optimized for that read performance. We can often peg the interface. We can often produce more throughput than the interface can actually transport. And hard drives can't do that. 15,000 RPM is at physics. It's about as far as you can go. Caching doesn't help you because we're talking about a lot of data that is strictly read, so read ahead gets me nothing. So the DRAM cache on the spin drive doesn't help. It must be because of the core design of these read-focused enterprise-grade SSDs, where really everything about the SSD is tuned for superior read performance and just getting that data out as quickly as is humanly possible. We aren't moving heads a lot in our rotating drives, right? It's sequential. The heads aren't flying back and forth. They're large transfers. We don't have a lot of encode decode on each end of the segments as they come off the drive. So it has to be that design tuning. You know, hard drives kind of have to do everything. They have to read, they have to write. They don't really benefit from workload-specific tuning the way SSDs do. And I think what you're really seeing here is the benefit of being able to tune an SSD to a workload, and the fact that we actually did it. In the 510 DC, we actually did that as part of the design.
Cool.
Does that help?
Yes, that does.
So that was a research example. One could say a theoretical example. Let's start our wrap-up by looking at a real-world example. So again, we're still focused on business intelligence decision support systems, and I wanted to call out Lenovo. So Lenovo has a data warehouse fast track focused on SQL Server. It's a reference architecture that uses another one of our enterprise SSDs, or M500. The biggest difference with the 500 DC versus the 510, the 500 DC is focused at more of a mixed workload. The 510 is focused more of a sequential workload. The 500 DC is more focused on, it has a greater write endurance, so it's more of a read-write usage model. 510 DC is more of a read heavy, write light. And I think one of the reasons that Lenovo chose the 500 DC is they really can't be sure exactly what their users are going to do with it. Its read performance is really, really good, but they wanted that extra, maybe that extra buffer, that extra margin of write capability, just in case somebody used this platform a little bit differently. But the net of it is, we're called out in the DWFT solution brief by name, by model. The things that Lenovo was looking for when they built this out, when they picked the flash drives, is they wanted to offer this pre-tested, pre-designed, pre-tuned, pre-set up, reference, buy it, deploy it type of configuration. In this case, it gets you to revenue much, much faster. There's no qualification involved. All of the components are designed and tuned to work with one another. What it enables the user to do, it really, your price performance ratio goes up. You've, again, spent very little time in trying to set up the box or manage the box. You deploy it very rapidly. You rack it, cable it, place the data, and go. You don't have to worry about things like proper drive selection or matching my DRAM to my CPU count and CPU type to how many drives I have. And frankly, it's much, much lower risk. The entire platform is fully validated by Microsoft. This was really an optimized design. This is pre-configured around their 3550 M5 platform. And again, if you go to the DWFT and read through it, you'll see a lot of the benefits that one gets. And you'll also see that, again, we're called out by name as one of the ingredient components. So the net value of this is it's much better TCO. Again, it's better performance using SSDs like we saw before with the 510. The similar benefit comes across here. It's much less expensive to deploy in terms of what results you get out of it, and also because it's completely pre-tested. And you have much lower OpEx because you get your stuff out faster. So if you look at OpEx in terms of how much time, the value of the time you spend waiting for results, enterprise SSDs are able to drop your OpEx as well. Again, they did select one of our enterprise drives, which has our Expert, XPERT feature set. This is a enterprise unique feature set. It's kind of like a list of options that design engineering can select from when they're building an enterprise SSD, and it helps them really tune the drive design around how we anticipate it's going to be used. And the M500 has Expert in it. It's much easier for anybody to support because it uses a standard SATA interface on the drive, which plugs right into the controllers in the system. And so, again, if I would encourage anybody who's interested, go out and take a look at the DWFT. It's got published results in terms of how quickly the data comes out using standard benchmarks that Microsoft requires. And the platform, again, fully validated by Microsoft. So this is just wrapping up pretty much what I just said on that one. It's go check out the DWFT. They selected this drive both for performance and durability. Again, my hunch is it's probably because they weren't really sure that it would get deployed in a read-heavy type workload, so they wanted that extra write margin that the M500 DC brings. That's why they selected that drive. And naturally faster time to revenue because it's easier to deploy, faster to deploy. And here's a link to the DWFT that's posted as a Redbook. Lenovo has gone public with that, made it available to anybody who wants. There's no sign up. There's nothing like that. You can go to Redbooks and get it. I believe that's also on the resources page towards the end. It makes an interesting read. So just to kind of wrap things up. Go ahead.
No, I bet the Redbook is fascinating.
Well, I guess it depends. If you like my boys and you'd rather read the Hardy Boys, a DWFT on Redbooks is probably not your cup of tea. But on the other hand, if you want to do this, if you want to deploy this pre-configured DWFT platform, go check that one out. It tells you what you're going to get before you cut your PO. It's really very straightforward.
Yes, this one is the Hunger Games of Redbooks.
Okay. I haven't read that or seen the movie, sorry. If we look at, just kind of to wrap things up now, there's lots of different ways people deploy SQL. We only looked at two of them. There's a plethora. And the two we looked at do kind of sit on opposite ends of the spectrum. If we look at OLTP, again, we think small, random, read to for every one that we write. If we think business intelligence, decision support systems, or BIDSS, we think large, sequential, almost exclusively read. Some of the benefits with OLTP, we saw that 75% lower CapEx in that example with 10 times better consistency and 10 times lower latency gave our IS group plenty of headroom to manage unforeseen demand, plenty of headroom for growth. The administration was really simple. You support it just like a hard drive. The LED warnings on the front light up just like you would expect with a hard drive. If we looked at how much work we could throw at one of our PCI Express drives, we saw that one drive with 160 people hitting it simultaneously was able to generate 2.5 million transactions per minute and north of 500,000 new orders per minute. And it did all of that with sub-millisecond write latency once we passed the ramp-up time. So that's great performance, one drive, great latency, just one drive. Over on the BIDSS side, the 510 really surprised us no matter what configuration we picked, even cutting the number of physical units in half compared to an enterprise disk array. We saw some advantages there in terms of query completion time, 75 to 85% faster for the same query set with the same users generated against the same database. And what we found was that was closely tied to storage engine throughput. And we saw about 5 times better throughput from the 510. The performance and durability, I mentioned the expert feature set that's present in all of our enterprise SSDs, and in particular, how Lenovo chose the 500 DC with the expert feature set. And then that really, that pre-configured, pre-qualified, Microsoft-approved platform enables whoever buys it to get to revenue faster with the additional headroom and durability that the 500 DC brings to it. So at this point, Matt, I think we've got 2 or 3 minutes left. If there's any questions or anything we wanted to follow up on or dwell a bit more, I'd be happy to field anything.
Okay, I think we do actually have one question online. We've been discussing adding and installing SSDs.
Yep.
Is there any upgrade of server DRAM? How much of a factor is server DRAM going to be in getting the performance out of your SSDs for SQL?
It's a great question. So the short answer is always, well, it depends. The long answer is you can get a good handle on that if you look at some of the performance counters that are available inside the OS. It's really hard to say, if I double my DRAM, I expect this much more out of the same SQL database, same query structure, same I/O load. One of the key differences would be the newer versions of SQL that support in-memory processing, I think the code name on that was Hekaton. If you bump your DRAM astronomically and you deploy that, you will naturally see a significant benefit, but it's not because of flash drives. It's because you've moved from an I/O-intensive permanent storage mechanism to doing the vast majority of your I/O processing in DRAM. But again, it's difficult to put a hard number on it, and each deployment is going to be different. My suggestion would be start small, pick a reference system to test on, ensure that you keep all other variables constant, and do an upgrade and monitor the application level performance. Run it for a while, and maybe do a subsequent upgrade and do the same thing. Naturally, you could feed it artificial stimulus as a good proof point, or if you monitor it long enough that you normalize out any traffic peaks, you could even use it in a real-world deployment. But that's a long way of saying lock as many variables as you can, make your judgment based on facts, make your judgment based on performance monitors that are standardized, and I would say start slow and build up so you have a few data points. You can then trace the application responsiveness and I/O throughput as a function of upgrade, and again, let it run a while so that you normalize out any peaks.
Gotcha. So yeah, basically.
Go ahead.
Yeah, it's basically you run some you can run some tests and see with your workloads if the extra DRAM would make a difference.
Exactly.
But minimize your variables.
In general, it will, but it's very, very tough to predict how much of a difference it's going to make. And again, it's because everybody's deployment is slightly different. What I would probably not do is go cut a PO for a giant pile of DRAM, install it everywhere with an expectation I'm going to get, 2 to the n performance out of it. I tend to be a bit more conservative and fact-driven. So that would be my approach if it was me.
But even still, all the experiments that we've shown, even in this webinar, the amount of DRAM was held constant. So all of the performance improvements we're seeing is strictly just because of the SSDs.
Correct. For all of the research data, that's absolutely true, even to the point where once the database was initially created, we backed it up to a shared location, and then we restored it before we started the next experiment. So we even normalized out any sort of changes to the database that would occur just as a natural process of measuring it. So we always have exactly the same starting point. The one exception to your statement would be our IS group, where they did a cutover. They did it, again, with one system incrementally, prove it out. They did it with another, then they rolled it out to a few more and a few more. In that case, there were significant changes. By moving off of multi-port fiber channel attached SAN, we don't have the overhead of fiber channel administration. We don't pay the fiber channel tax per server, where you need at least one HBA with at least 2 ports per system. So that expense is gone. But in terms of keeping variables constant, they intentionally simply place the database from the SAN over to the 2 U2P systems in an HA mirror, and change nothing on the underlying data set and change nothing on the query structure. So from their perspective, it wasn't a spin drive to flash drive swap out. It was a storage mechanism or design to a new storage mechanism or design. So I guess you could say they only changed one variable, but it's a gigantic variable.
And it made a huge improvement. Well, Doug, thank you. I think we're getting low on time, but thank you again. It's a treat. It's always a pleasure to talk to you, Doug. Hope to have you back for another webinar.
Thanks for setting this one up, Matt. This was a lot of fun. Looking forward to the next one.
And remember, if you'd like to contact Doug, or just use the email or LinkedIn icons on the speaker bio to connect. Plus, you can also follow all of Micron's flash storage activities using the @MicronStorage on Twitter. And thank you to everyone who joined us today. As a reminder, you can register now for our next Micron Value Partner webinar coming up on Thursday, September 17th at 3 p.m. Eastern. We'll be joined by Mike Tomke, Micron's Senior Product Marketing Manager for the Enterprise Solid-State Drives, who will be introducing to you the new Micron S600 SAS series of SSDs. creating a cost-effective hard disk drive replacement for enterprise performance storage. You can use the webinar registration link in the resources section of your webinar window to sign up now for the new product introduction that's coming up Wednesday, September 17th. So until then, I am Matt Wokus, and on behalf of the entire Micron Storage team, thanks for joining us and having a great afternoon.